So hello everyone. So my name is Barbara Simpson. I'm an assistant professor at Oregon State University. And today I'm going to be talking to you about developing real-time hybrid simulation for wave structure interaction. And these developments have been ongoing for a few years now. And although I'm presenting this work, I really should mention that this is the result of a number of different collaborations between different universities and people from a number of different expertise in different disciplines. So I'm trying to, at the bottom, you'll see a citation or a reference for the ongoing collaborations for many of these projects. So just to give a general outline of what I'm going to go through today, so I'll just start out with like very, very bare bones history of hybrid simulation, the facilities that we have here at Oregon State, this idea of real-time hybrid simulation for fluid structure interaction problems, which is really the meat of this presentation. Some challenges that we're dealing with sort of implementing hybrid simulation for wave structure interaction, the hybrid simulation setup that we have here at OSU, and some ongoing projects. And at the very, very end, I'll then give a much needed shout out to, I can't emphasize this enough, the number of different collaborators who have participated in all aspects of this ongoing work. So let's start out history of hybrid simulation. And I like showing this slide because it goes to show you how much times have changed. So the original sort of online testing method for hybrid simulation, the first publication, came out in 1975. There's of course been a number of instrumental works that were also from the late 1970s, 1980s. And you think about how much computational power we have now compared to back then, and it sort of gets you thinking about what other problems we can start addressing, particularly with the growing emphasis on multi-hazards engineering and research. And so when we think a lot about hybrid simulation, we often think about it in terms of earthquake engineering problems because that's where it was originally developed. So hybrid simulation, the entire sort of idea is to take a model and split it up into some sort of numerical component that is communicating with some sort of physical model in an experimental facility. And this numerical and physical model then are coupled through the equations of motion or whatever relevant physical equations there are to couple these two systems. And then based on that equation of motion, you solve for the next time step, which will give you some sort of, based on an input motion, some sort of numerical and physical command in both the numerical model and in the physical experiment. And then what you'll do is you'll, based on that numerical displacement, for example, you'll measure some sort of virtual resisting force in the numerical model or from some sort of sensor in the physical model, and that feeds back into the equations of motion to then solve for the next time step. So you're really, this hybrid simulation concept is combining a physical and numerical component. And then since you're actually testing a portion of the system in a physical laboratory, you can then say that you're combining the advantages of both worlds, numerical and physical, to somehow get to a more realistic response. So that's sort of the meat or the idea behind hybrid simulation. So how do we start thinking about it in terms of fluid structure interaction or wave structure interaction here at OSU? So we do have structural testing facilities here at OSU. We have a recently open mass timber structural testing facility. We also have a structural testing facility. But what I'm going to focus on is actually this sort of facility right in front of our structural testing lab, which is really sort of the unique wave Flume and wave Basin facilities that we have at OSU that really are leveraged when you're talking about hybrid simulation for wave structure interaction. So these are the largest coastal facilities at a US university. And I'm sorry, I see that there's like an orange button flashing that there's comments. So I'm going to wait till the end and hopefully be able to answer some of those. So we do have a large wave flume where we can test at fairly large scale. And then we also have our wave Basin facility here at OSU. And these are a part of the NHERI sites. So if you have an NSF grant, you do not have laboratory fees to test at these facilities. And there's a number of different things that you could start looking at when you're thinking about wave structure interaction. I've just listed a few of these here. Nearshore hydrodynamics, tsunami research, coastal structures in terms of fluid structure interaction, sediment suspension and transportation, or transport, environmental fluid mechanics, floating structures, and the list goes on and on. And then I've just kind of listed in the side here, you can start thinking about studying surge or wave impact loading under a hurricane. You can also think about tsunami inundation and the fluid structure interaction effects that go with that, as well as one of NSF's 10 big ideas right now is navigating the new Arctic. And so thinking about sort of how we can start leveraging this facility in a new way in terms of multi-hazard engineering and in terms of hybrid simulation, it kind of all of a sudden becomes a little bit interesting. And so when we think about what we're able to test in a facility like ours, and we think about all the things that we want to test, we're often thinking about scaling. And so we have a wave flume and a wave basin that only has a certain amount of space and a certain level of capacity, which means that almost everything that we're going to conduct in our facility or test in our facility is going to be at small scale. So when we look at, for example, this was a test that was a 1-to-1 scale, but it's only a portion of a structure or a partial subassembly, or we can start thinking about testing a house, but again, that house becomes small scale. And then if we start talking about towns or cities or regions, that of course comes even smaller scale still. And so when you start thinking about how hybrid simulation can come into play in a facility like this, you really start thinking at, well, how can hybrid simulation mitigate some of these scaling loss or mitigate some of these scaling effects? So in a lot of the cases of these experiments, you're either making simplified or idealized boundary conditions. You're also, when thinking about scaling, you're often scaling according to the fluid and not necessarily towards the structural dynamics. And hybrid simulation is a concept that could help you mitigate some of these similitude requirements. So this is sort of the experimental testing that we're looking at OSU's facilities. So this is a recent experiment that sort of demonstrates this. So on the left, we have a bridge deck, and it actually is set up with a spring. So when the wave hits this bridge deck, there actually is a fluid structure interaction component that includes the structural dynamics from the spring. And what these researchers did was then, based on load cells that they measured during this experiment, they then took that history of that history from the load cell and then applied that to a full-scale bridge specimen. And so they're already starting to think of hybrid simulation, not so much as how we traditionally think of it in earthquake engineering, as combining a numerical component with a physical component through the equations of motion, but you're thinking about it in terms of combining maybe hydrodynamic testing with full-scale structural testing. And so we can start thinking about hybrid simulation as something more than what we've traditionally thought about it in earthquake engineering. And these results are very interesting, mainly because of this figure on the left and looking at the actual dynamics of this bridge structure. What they found is that it actually influenced response quite a bit. And so on the left, you have, instead of that spring, they basically have a rigid boundary. So you see that the bridge doesn't move. And then on the right here, if I can get it to play, you can actually see that fluid structure interaction effect and that this bridge deck actually undergoes fairly large displacements that are affecting the response quite significantly. So they have the horizontal force versus time in both these figures on the right, and you can see the difference between the rigid response and the response that takes into account structural dynamics. And the structural dynamics can actually lead to larger forces than you would if you had just modeled it with a purely rigid specimen. And as you'll see later, similar testing was also done by Dennis Israti and Ian Buckle at University of Nevada, Reno, and they found also very similar results. So if you want to start taking into account the actual structure characteristics, the structural dynamics, you need to somehow get around these scaling effects because oftentimes hydrodynamic experiments are conducted at small scale and neglect a lot of the physical characteristics of the structure. So that leads to this idea of hybrid simulation for fluid structure interaction problems. So the idea of hybrid simulation, combining two things, a physical and numerical component, that stays the same. But then we can really start thinking about how we want to model this physical part and this numerical part, and how we can combine them in different ways to come up with more unique answers. So the setup that often is sort of shown is that you could have some sort of structural model, and that structural model can be at full scale, right? Because it's all numerical, it's in a finite element analysis. And you couple that structural model, and then based on any displacements from that coupling, that you then send that as a command that are scaled down by whatever small scale that you're looking at, say for this orange bridge pier on the right. And then when you have some sort of sensor that's measuring the response of that bridge pier, that can then be scaled up by Froude and fed back into the coupled equations of motion. And so you can imagine that because the structural model is at full scale, you can actually combine inelastic response at full scale, realistic stiffness properties, damping, for example, and then you can combine that with something that's small scale in the wave basin or in the wave flume. So you get around a lot of the similitude effects. Now here's the problem. As much as I would like hybrid simulation to be like this, the fluid is actually always going to run in real time. There's really no way, well, no accurate way potentially of slowing down the fluid dynamics. So if this coupling is going to occur simultaneously between this numerical model and this physical model, it really has to be done in real time. And that really is the true challenge of implementing hybrid simulation for a fluid structure interaction problem, because whatever the fluid does, your structure has to interact to that fluid in real time if this numerical model is communicating with this physical model simultaneously. And so one can consider several scenarios for sort of thinking about fluid structure interaction. So we have a numerical component that could be made up of a partial structural specimen. The numerical component could be the wave. If you're thinking about fluid structure interaction in general, you could start thinking about the numerical component as being wind. And then in the same way, you can think about the physical component as being any one of those things. And so when we're thinking about partitioning a wave structure or fluid structure interaction problem, you're really thinking about where are you cutting the system between the wind and the wave or the structure. On top of that, you can start thinking about multi-hazard scenarios. So you could think, what if you are interested in cascading hazard? So you have an earthquake and you numerically damage the structure for seismic loading, and then you subject it to a tsunami in, say, the wave flume. So you can start thinking about hybridizing numerical and physical components in a number of different ways. So let's look at that first one, and I'm going to call it the traditional scenario, where you have a physical subassembly that's the wave and a partial part of the structure, and then that's going to have a numerical subassembly that's the remaining part of the structure. And you'll notice that I'm calling them subassemblies instead of substructures. In the literature, oftentimes when you're partitioning this set into numerical and physical components, they're often referred to as substructures. I'm just using subassembly in this case because you're also including the wave as part of it's the wave plus structure. And so we look at this traditional approach. What we're doing is we're taking a complete assembly, let's say of a building that's being impacted by tsunami loading, and you're splitting it up into two parts. And one part is going to be the physical subassembly, and then the other part is going to be that numerical subassembly. And combined, it represents the response of the complete building. And basically, the hybrid simulation component is at the interface of this physical and numerical part. You enforce the interface conditions, so the interface forces, and then as well as compatibility between the displacements. And so this XP and XN, which are the physical displacements and numerical displacements, actually reflect the displacements of the system as a whole. So that's sort of the traditional approach, and there's a number of advantages to sort of thinking about just having a numerical model extend your existing facility. So if we start out and go back to that bridge deck example, If we're thinking about sort of a rigid bridge deck, we're not capturing that structural dynamics. We could, of course, think about implementing some sort of spring, exactly like that previous study did, where we can then have some structural dynamics that have interaction between the structure and the fluid incorporated into our physical experiments. But we could actually go one step further, and why not just replace that single spring with a single stiffness with some sort of actuator that's able to represent an infinite range of stiffnesses. And if you're going to put an actuator there, why not just take it one step further and really virtually extend your wave facility? So you can see that by implementing hybrid simulation for wave structure interaction problems, you can actually test something that's infinitely more sophisticated than you would if you were just thinking about it only being an experimental facility, because now we can test an entire bridge rather than the bridge deck. And so you're really increasing the sophistication of your bridge model. So that's this sort of traditional approach where your numerical model is really the remaining part of your structure, and then that's interacting with some sort of component that you're testing in your physical facility. Now, what are the advantages of this? Well, and this is a very important point, assuming that you know how the structure is modeled and you're really confident in your structural part of the model, then you get a really efficient testing of the wave. Because if you think about computational fluid dynamics problems, they're very computationally expensive. It's a very difficult computational environment. And so you can actually run a wave, an order of magnitude, I'm saying order of magnitude, but really much faster in a physical sense than it would take to actually do it computationally. So you get efficient testing of your wave. The wave itself is actually also still there in physical, and the way it interacts with the structure is also physical. So you're also reducing uncertainties because you're modeling this very complex interaction between the wave and the structure physically. Like you're not making any assumptions about that interaction other than the assumptions that you would typically make in any sort of experimental test. On top of that, on the numerical side, now you get all these additional complexities gained through the numerical model. So you could start looking at something that's much bigger or more complex than you would be able to test on its own in a wave facility, just because we have size limitations when it comes to the Flume and the Basin. You can also think about having that structural component at full scale. So that means a lot of the structural behaviors and responses are at full scale, and then it's interacting with the fluid at small scale. So you're able to mitigate a lot of similitude requirements. On top of that, you can swap out this numerical model quite easily. So you can imagine testing a number of different structures or different parameters in the structural model, all by using the same test setup. So you're getting a lot of efficiencies gained by sort of this coupling of numerical and physical components. So that was the first sort of traditional, the remaining structure is modeled numerically, but then in your facility, that wave structure interaction is modeled physically. The traditional sort of approach could also be reversed. So we could think about the same sort of scenario, but instead of the remaining structure being physical, the remaining structure being numerical, we could flip it. And we could actually say that our wave is going to be numerical. That's going to interact numerically with some sort of structure. And then the remaining structure is going to be physical. So what that would look like is maybe something like this. And so these are some photos that I actually borrowed from another presentation. But you can imagine now that the fluid is actually a computational fluids model that's applying some loading to a structure. So it's sort of the reverse of what I had previously shown. And so now you can start thinking about a number of different ways in which you can partition the system. Now, all of this becomes a little bit more complicated when we start doing fluid-fluid structure interactions. So for example, in hurricane loading, we're often not only interested in the waves, we could also be interested in the wave, surge, wind, and structure interaction. So you can imagine a number of different scenarios where you're combining not just the structure and say one fluid, but the structure and multiple fluids. So for example, we could think about a physical subassembly where we take a wave and a partial structure and we model that physically in a wave basin, and then it's going to be interacting with a numerical subassembly that could be the wind that's modeled numerically and the remaining structure. And so what you start really getting into is combining all these different scaling laws when you're starting to deal with multi-physics problems like this one, where you have, in this case, I have an elevated structure being subjected to waves, structure, and wind. And so when you scale something down into small scale in a wave basin or flume, you're wanting to satisfy several conditions. One is that you want it to be of similar shape, and so whatever you have at full scale, when you scale it down to be small scale, you want it to follow geometric similitude. You also want to have kinematic similitude, where you have similar velocity and flow of the fluid at small and full scale. And then really the big one that I'm going to sort of focus on when it comes to hybrid simulation is dynamic similitude. And that's just saying that the forces, or at least the forces that are relevant at small scale, you want them to align with the forces that are at full scale. And really the issue with doing something like this, a multi-physics problem where you're dealing with the wind and the structure and the waves, is that each one of these components actually, you're interested in different parts of this dynamic equation of motion. And so that means that if you are going to focus on the similitude law that emphasizes the parts of the problem that you're most interested in, they're going to be different similitude laws for the wind, the structure, and the waves. So for example, for the wind, you're looking at Reynolds number scaling, which is basically saying that at full and small scale, the relationship between, or the ratio between the inertial and the viscous forces is equivalent. So that means you're saying that ratio is important to your problem for wind loading. For waves or open channel flow, you're often looking at Froude scaling, in which case, instead of the viscous forces, you're interested in this ratio between inertial and gravitational forces. And then finally, for the structure, you could follow Froude scaling, but you could follow a number of other similitude requirements. For example, Cauchy scaling is the ratio between inertial loading and elastic forces in the structure. And so if you're looking at a small scale experiment, you only get to choose one of these. And so that means that the scaling for all the other parts of your problem are not necessarily compatible for the scaling law that you choose. So for example, if we were to choose Reynolds scaling, I've plotted the time scale on the vertical axis and then the length scale, how much you're scaling down on the horizontal axis. And basically to make sure that Reynolds number is equal to, so that your inertial to viscous forces in the full scale and model scale are the same, you have to change the time scale. And so this just plots that relationship with respect to Reynolds scaling, which is for your wind. If you do the same thing for your waves, now you're looking at this ratio of inertial to gravitational forces. And so then you have a different relationship with time and length. And then finally, if you're saying that you want to plot your structure according to Cauchy scaling, then you get another relationship again between time and length. And really the only time that these similitude laws have equivalent time scales is when you're at full scale. So any deviation from full scale, you're dealing with incompatibilities between the scaling laws. And just what that means is when you're looking at the dynamic equations of motion, it means that you're getting one that has equal forces between the full scale and model scale, but then the other forces will shift based on the similitude law that you employ. And so because of this, I mean, even though you want perfect dynamic similitude and you want the dynamic equations of motion to be the same in the full scale and small scale model, it's actually impossible to do all of them. And so you often do sort of partial similitude, where you select one of these and scale your experiment by one of these laws. And so when we start thinking about facilities where you have fans applying wind over a wave basin and you're using a small scale model, and I just am showing 3 here, you're actually subject to incompatibilities between the scaling laws used for the wind and the scaling law used for the waves. And I'm disregarding the scaling laws for the structure entirely. And so you can actually say, well, maybe even though you're applying wind in a wave facility, that dynamic similitude between the wind and the waves is not quite correct. On top of that, you're dealing with difficulties in applying wind in this way. So you'll notice that in these cases, the fan is very, very close to this model of this offshore wind turbine. And that's because they want to get there's only like a small volume in which you get a fairly good wind field in front of this distribution of fans. And so you want to make sure that you're able to represent that, but it's only in a very, very small volume within this wind flow in this wave basin. So there's all sorts of difficulties when thinking about how to apply wind and waves, both physically in the same wave facility. So instead, you could maybe think about it in terms of a hybrid simulation approach. So this is a project recently funded by the Department of Energy, and so you can think of a floating offshore wind turbine physically modeled in a wave basin, but instead of trying to get around any similitude requirements between applying wind and waves, both at small scale, both in a physical setting, you can say, I'm gonna model the wind numerically. In which case, the numerical wind and maybe any sort of properties associated with the structure could be at full scale and interacting with whatever specimen you have floating in your basin, which is scaled by Flume, which accounts for those gravitational forces that tend to dominate the response when you think of like wave loading. So this is one way of sort of thinking about this problem of similitude. You can think about it in the opposite sense. So instead of having the wind be numerical and the wave be physical, we could flip that around, and we can have the wind be physical and the wave be numerical. And so what that might look like in a wind tunnel facility is you have, again, an offshore wind turbine, but instead of the wind being numerical, you have the wave be numerical. And so now this Stewart platform is actuating the motion of the wave, which is then causing this floating offshore wind turbine to move, which then affects the wind flow where the wind flow is physical. So there's lots of different ways that we can start thinking about partitioning the system in terms of numerical and physical components. We could take that one step further and we could say, well, rather than have any component of this system be numerical, what if we just want everything to be physical? In which case I want a physical wave and a physical wind, and then I'll have a partial structure in a wind tunnel, and then the remaining structure will be in the wave basin, and that'll all be coupled. And so then you can start thinking about having two separate facilities, maybe testing at fairly large scale. So for example, we could have the wave basin or the wave flume here at OSU, and then we could think about modeling the wind at the wall of wind at say one of the other NHERI sites. In this case, I have Florida International University, so wall of wind. And then you can imagine some sort of communication occurring between Oregon and Florida, where whatever we're doing in our facility is according to fruit scaling, and then we're coupling that in some way, potentially through the structure, to whatever is being done at a wind facility, which is using a different scaling law, or, if possible, at full scale. Now, the issue with this is that you're talking about really, if you're still dealing with a real-time hybrid simulation, then you're talking about real-time communication between Oregon and Florida International University. And as I stated previously, because everything's at small scale, you're actually dealing with faster than real time in a lot of cases. So doing the communication to have both both fluids interacting with each other through the structural model in real time, when you have a very large facility at Oregon and another geographically distributed facility in Florida is very difficult. But you can start thinking about this problem in a different way. So for example, if we're thinking of this elevated house again, where we have the waves, the structure, and the wind, we can maybe start thinking about more of like offline hybrid simulation approach. So for example, we could have a portion of the structure that's submerged at a wave flume or in the wave basin, and then you can still have the same model with the same geometric characteristics in the wind tunnel. And you can imagine measuring the wave profile and the surge height at the wave facility, and then having some sort of offline actuated boundary layer at the wind facility. And so you're assuming a lot of things here. Number one, you're assuming that the wind is not, that interaction between the wind and the waves is negligible. And you're also neglecting a lot of the structural deformations and the effect that might have on the wind and wave flow. But if you were to do this in this sort of offline environment, you could then measure pressure histories at the wind tunnel or the wave flume or basin facility, and then you can take those pressure histories and apply them into some sort of deforming structural model. And in this way, you have you can have different scaling laws for all parts of your system. So you could have your wind be for Reynolds scaling, you could have your wave be for Fruit scaling, and then when you go and apply that offline to your structural model, that could actually be at full scale and have full scale structural characteristics and dynamic properties. Now the issue with that is you're making an important assumption, and that's that your deformations do not necessarily affect, the deformations of your structure don't necessarily affect your fluid flow. And so actually doing the reverse of this, where by deforming, the fluid actually is also affected, and this would be the case for any sort of high damage situation or any structure undergoing large displacements, which would also affect the loading conditions. That's not taken into account in this sort of scenario where you're going from one side of this problem, one side of just loading to the other side, where you get the structural deformations. But this could be one approach when thinking about coupling geographically distributed facilities. So rewinding a little bit and starting to think about challenges. So there's a number of reasons for why you would want to do hybrid simulation for fluid structure interaction. One is you have these physical models. I think I've stressed enough that those physical models are at small scale, and it's very difficult to scale the fluid along with the structural properties. And if you're combining multiple fluids, that similitude becomes even more difficult because you have different scaling laws that sort of govern, for example, wind versus waves. You're often neglecting potential structural dynamics effects or fluid structure interaction effects, which could be non-negligible, as you saw at the very beginning of this presentation for that bridge experiment. And so you could really say that because of this, because we're not able to test at full scale, that data is limited for certain types of problems. On the computational side, you're dealing with a very uncertain environment. It's very computationally expensive, and at the end of the day, if you're building a computational model, it needs experimental validation. So when you think about the question, why hybrid simulation for fluid structure interaction, it's because of this paradox between the physical models and the computational models. So you need physical models, you need physical experiments and physical data to validate your computational models. But your physical models might not necessarily represent full-scale structural response because of the many simplifications that we need to consider when testing, including idealized boundary conditions, small-scale effects, etc. And so there's a need to do hybrid simulation for fluid structure interaction problems, but it's not exactly simple. And so there's a number of challenges that need to be considered. So while hybrid simulation can be considered mature for, say, earthquake engineering applications, when we're thinking about wave structure and applications, we have to think about a few other things. One is this real or faster than real time. So again, since the fluid is not going to slow down for you, if you want your numerical model to interact with your physical model simultaneously, then it has to be satisfying the equations of motion or solving the equations of motion in real time, or even worse, faster than real time, due to similitude requirements. So as you scale down your model to fit in your flume or basin facility, you're also dealing with a time scale that also shrinks. meaning that, again, it has to be faster than real time. So whatever computational model you have, it has to keep up with what's happening physically, unless, of course, you do something offline, like what was presented a few slides earlier. So this becomes really problematic when you're starting to think about model parts of this problem numerically when it's the fluid. So depending on the numerical model, or if you're modeling computational fluid dynamics, that's typically slow. And so thinking about how that numerical model can keep up with your physical model is difficult. Now there's a number of different models that you can use for the fluid flow. And you know, I'm going to leave that kind of as an open question, but this is definitely one of the primary challenges that I consider when thinking about wave structure interaction. Real-time, for real-time hybrid simulation. Of course, if you think about a couple of the other application I gave, where you have the numerical model interacting with the physical model, where the physical model is the structure and the numerical model is, say, the wave or the wind loading, then of course you can slow the time scale down to whatever you need. But when you're thinking about real-time hybrid simulation, it needs to be fast if a wind or a wave component is modeled physically. The other thing that you need to consider is that these wave structure interaction problems are not like the typical problems that we see in earthquake engineering. First off, you're dealing with a pretty high frequency pressure effects. A lot of the collaborators that I'm collaborating with would rather do force rather than displacement control. It all depends on the problem, of course. On top of that, you're dealing with forces that are very much smaller than the forces we deal with in very large scale structural applications. And so a lot of this could potentially be mitigated by the fact that if you have a flexible structure, you'll actually get a different set of frequencies in the force versus the pressure response. And so a lot of that high frequency sort of response goes away. And this was seen extensively by Dennis Israti, who did very similar experiments to what was done with that bridge and the spring that I showed earlier in the presentation. So you get this is alleviated somewhat if you actually incorporate the structural dynamics into the system. But it's still something that needs to be considered, and it is something that can be difficult on the control side. But the third thing that I really want to emphasize is the fact that this is all being done in water. And so anything that you do really has to be waterproof, and any equipment that you have really has to be protected. So in a lot of cases, the typical actuation schemes that you would use for earthquake engineering, including hydraulic actuators that supply very large forces, might not necessarily be the same sort of actuation scheme that you want when you're dealing with a water setting where you don't want any oil to mix in with your water, and you're dealing with much smaller forces, and you want your actuator to be potentially waterproof if it's going to be submerged in any sort of way. So thinking about that is definitely something that can be a bit challenging. And so we've attempted to address all of these challenges here at Oregon State. So when we think about our setup, we already have a wave basin and wave flume here at our Hinsdale Wave Research Laboratory. And so we can start thinking about an actuation scheme that, number one, is placed so it does not affect the fluid flow, but number two is also waterproof. And so we've actually, we have a custom waterproof electric actuator, so it's electric instead of hydraulic, that we've purchased to actually do hybrid simulation. And you'll notice that I've listed the forces, the stroke, and the speed here. And the force is that 10 kips is actually on the high side for a lot of what is seen in hydrodynamic experiments. So you're looking at a waterproof electric actuator, so it's not exactly the same dynamics as you might see from a hydraulic actuator. And then that's being controlled through some sort of controller and data acquisition system, where it's sending, in the case of displacement control, some sort of command signal, and then measuring some sort of force on this partial specimen. And then that's communicating on the other side with the remaining numerical model And then we have a simulation host computer, which we're using the OpenFresco approach. So the OpenFresco middleware is also housed on the simulation computer along with your finite element analysis software that is emulating the numerical parts of the model. And then because your sensor control loop might be operating at some sort of deterministic timescale that's different than the timescale used in your numerical finite element analysis, then you can imagine some sort of rate transition loop or predictor corrector loop being housed on a real-time target computer in the middle. So at least for right now at OSU, we're using this this 3-loop architecture to conduct our hybrid simulation experiments. That doesn't mean that we can't do something else in the future. This is just what we've had right now. And so how these are all coupled together is that we then have the ScramNet shared memory network with fiber optic cables that is able to have real-time or fast communication between each one of these components. So as far as the hardware that we've implemented at OSU, fairly traditional, and this sort of architecture has been well documented in past studies. What might be a little bit different is the fact that our computers glow in the dark. So on the left here is Andreas Schillenberg, so he's been working a lot with us and implemented hybrid simulation here at OSU. And then there's a figure of me next to these 2 giant computers, our target and host computers on the right. And basically these are custom machines that Andreas and I built together. And I just feel like I need to show this image because I'm rather proud of them. But they are very fast, and they are faster than the current SpeedGoat machines, and we're hoping to have documentation for this that's online and open source soon. And so that leads to the final part of this presentation, and I already feel like I'm talking really fast. Okay, I'm still good on time. That's good. I should have slowed down a little bit. So let's talk about ongoing projects here at OSU. So I'm only going to talk about two significant projects that I've been involved with. All of them have been fairly multidisciplinary, and so when I think about where I am on this wheel, and this was the wheel that was in the research agenda put out by MEX, and I just loved it so much that I show it in almost every presentation that I do now. But I'm really on the structural side of this wheel, but there's of course a lot of different disciplines that go into thinking about hybrid simulation problems. On top of that, you're dealing with this fluid component. And so it's not just the structural dynamics that you're dealing with, it's also the fluid dynamics. And so I've been interacting with a lot of coastal engineers, wind engineers, as well as electrical engineers. And it's interesting how the language between all of us is so different. And so really thinking about hybrid simulation in terms of a multidisciplinary endeavor is really important, and being able to communicate ideas, because what you'll find is that you're talking about the same thing, but because someone's in a different discipline than you, you don't quite understand what they're trying to say. So implementing hybrid simulation for fluid structure interaction requires a multidisciplinary team of people with very different backgrounds. Now, here at OSU, if we think about the classic sort of hybrid simulation classification, and I've sort of touched on all of these when I talked about the applications, we're really sort of dealing with this from a real-time standpoint, where the numerical and physical components are co-located at the same facility, although I did talk before about geographically distributed hybrid simulation. And then we're also approaching it from that 3-loop architecture. And so just to give you an idea of what's coming up, we are expecting to test in December 2020, a sort of pilot test for hybrid simulation, real-time, and fluid structure interaction problems. And there's a number of different collaborators involved in this project. And I just really want to point out that Christopher is the graduate student working on this project. So even though I'm presenting this work, really, he's the main person working on it. But this whole setup for this pilot test is very much what I initially showed in those original photos. So we have a numerical subassembly, which is really the majority of a bridge. And then we have a pier and the fluid structure interaction component that's being modeled physically. And then they're coupled together through the equations of motion. So this is a very classic sort of approach approach to hybrid simulation. And as a pilot test, we think that it's important to sort of approach this problem from a traditional standpoint first. And so what we have is we have this existing physical specimen that was actually used for a previous NSF project. And that specimen is pinned at its base, and an actuator and load cell will be sort of supplying the remaining structural response at the top of that pier. And then our numerical component is, of course, the remaining bridge, but we're also gonna have some numerical modeling of plastic hinging at the base of the shaft, or potential sort of soil structure interaction characteristics. And what's interesting about the way that we're doing this model is that we can subject the numerical model to previous earthquake loading, and so get some previous damage state as if you had an earthquake loading first, and then look at it under tsunami loading in our wave flume. So that's sort of the premise of this project. And so you're able to do these sort of cascading scenarios of earthquake, and then you have a pier that's been previously damaged that you then test in the wave flume. And so this is just what the specimen looks like. And so again, you have that pin, and then we just have an additional load cell at the base that's not really used for the hybrid simulation, but it is there to measure what's happening at the base of the specimen. And then we have a wave that's impacting this pier that's already been damaged by the earthquake, and then we have an actuator plus the load cell that's sort of being coupled to the remaining numerical model. And so the numerical model that we're using is actually an existing numerical model that's been documented by many others. But what's kind of interesting about the numerical model is the way we've done it. So we do have a pin at the base of this experimental specimen. So we need to make sure that this numerical model plus physical model actually satisfies equilibrium. And so we have a spring that's being modeled at the base of our numerical model that sort of represents any sort of plastic hinging from previous earthquake loading, or any soil structure interaction effects. We also have the remaining bridge deck. And then the pier in the numerical model is actually modeled as rigid. And in that way, we can sort of condense out some of the degrees of freedom that we don't necessarily have in our physical model. We then have a load cell and an actuator at the roof of, this is not the top of the roof, at the top of the pier. We can then supply some sort of loading history through the wave, some sort of distributed loading, and then supply some sort of physical displacement, and then monitor some sort of force. And then based on this, we sort of, again, go back to the 3-loop hardware architecture where we were using displacement control, where we're supplying the physical pier with the displacement, and then measuring the resulting force, and then coupling that to this model of the remaining bridge. So that's sort of the pilot test that we're expecting to test this December. The other project that I've already mentioned is a project funded by the Department of Energy, and then the expected testing for this is spring 2021. And this is actually a significantly larger project that's made up of a very multidisciplinary team. I'm on the structural engineering side, but you can see from everyone here, we have a lot of different participants that have expertise in offshore wind and wave energy, mechanical engineering and energy, electrical engineering, coastal engineering, etc. So it's a very much a multidisciplinary team, and it's been very fun working with all of these different people. But it looks exactly like the figure that I showed previously. So in this case, we have a physical specimen, and this project's focusing on floating offshore wind energy. So we have a physical specimen located in our wave basin that's gonna then be supplied with some sort of numerical loading of wind. We're using OpenFast, which is an open source numerical analysis software from NREL, which is for offshore wind, or it's for wind energy in general, but they do have modules associated with floating offshore wind energy. And so that's going to be supplying the wind. And again, using that 3-loop architecture, we're supplying some sort of wind loading through some sort of actuation scheme through to our floating offshore wind turbine. And this was just the previous image that I showed but it's basically the same thing. Now, I'm showing the sort of cable system on how to apply the wind, but in reality, that's not necessarily what that actuation system is going to look like when we actually implement this. So we're thinking of a lot of different sort of actuation schemes. And the reason I wanted to show this slide is this figure on the right. So we're not the only people to have conducted this sort of numerical wind in an offshore, floating offshore wind turbine setting. And I've just sort of cited others, mainly in Norway, who have also explored this mechanism of hybrid simulation. And so I just wanted to end with this last slide. I think I've mentioned quite a few times that there's been a number of different collaborators that I've worked with, and I am by no means the only person who's been looking into this application of hybrid simulation for wave structure interaction. There's a number of current projects that have been funded and ongoing collaborators that have been working with me on all aspects of this project. So, you know, if you want to get in touch with any of these people, please either, I don't want to say reach out to them, but you can definitely reach out to me, and I'll definitely link you up if I can. And with that, that is the end of this presentation. And I noticed that there's been a couple people chatting, so I'd be happy to answer any questions. I can't hear you. Interesting. So does anybody have any questions? Yes. And I can answer, what is the minimum sampling frequency, and how do you determine it for these fluid RTHS problems? Yeah, and I would just say that that all depends. It depends really on the frequency of the structure that you're looking at. And as far as the controller, I mean, we have, let's see, we have a flex test controller, for example, that's 2048 hertz. And so the reason that we ended up implementing that 3-loop architecture is now you can have your numerical model at a different frequency than what's happening in your experiment. So if for some reason it takes more time for your numerical model to solve for a time step, you can sort of still keep sending commands to what's happening on the control side. Let's see. Now, when thinking about what's happening to the structure, that just it depends on a lot of different things. For example, it's the parts of the problem that you're interested in could be highly different depending on the frequency of the system that you're looking at. And there's a lot of different rules of thumb that sort of tell you which part of the fluid structure interaction, which part of the fluid structure interaction problem is important. And a lot of those have to do with like what sort of natural frequencies you have for the structure. For example, the mass number can tell you sort of whether your fluid or your structure or your fluid structure interaction component is important. There's something else called I'm trying to remember, it's been a while. I'll just leave it as there's a couple of different dimensionless numbers that you can sort of look at that gives you a ballpark of kind of which aspects of this interaction are important. Did you recommend any integration algorithms for RTHS in fluid? So I did not recommend any integration algorithms, and so I guess I should clarify, what do you mean by in fluid? So for the, I guess, while I'm waiting on that question, when you think about sort of this, the more traditional approach where you're actually partitioning at the structure level rather than the fluid level. So if you're partitioning at the structure level, then the integration schemes are really whatever you would typically use in any other sort of hybrid simulation problem. So there's a number of different fluid structures. So I guess, okay, again, I think maybe I'm misunderstanding the problem. So if we go to this one here, and maybe I think I like this figure better. If you go to this one here, where you're really partitioning at the structural level, then any sort of traditional hybrid simulation integration scheme that you would use for earthquake engineering still applies, because it's still on the structural level. And a lot of the approaches that we've been taking to fluid structure interaction has often focused on partitioning the structure for that reason. So anything that's been used previously or existing literature that's available for hybrid simulation and earthquake engineering can then still be applied to a lot of these fluid structure interaction applications, because we're focusing on partitioning the assemblies at the structure. So I hope that answers your question. I'm not sure if it does. You can feel free to unmute yourself too. So, and I guess I should mention the nice thing about partitioning that way, like in this case, for example, so your fluid is physical, but really you only have to solve for the structural portion. So you're just assuming that the fluid is applying some sort of loading condition, but you're not actually monitoring that loading condition directly. What you're monitoring is you're monitoring the structure's response to that loading. And so when you go and integrate the equations of motion, like it's done here, when you're integrating the equations of motion, really notice that this Q wave, this sort of pressure that's coming in from the wave itself, isn't really coming into this equation of motion that's coupling the two systems. It's really focusing on the structural part. When we're looking at some of these other problems, for example, this problem here, where you're dealing with something that's maybe not a classic structures problem, then you might be using a different sort of integration scheme. And actually, we're still in the process of sort of looking at how this coupling is going to be performed in this case, and whether it's going to be displacement or force control or something of that nature. But I guess as far as this question, oh, now there's other questions earlier about the fluid structure interaction and the fluid structures integration scheme. Really, the fluid only comes into play in sort of a classic sense. And so when you're looking at this set of equations of motion, you're really only monitoring the structure's response. And so it's just a classic structural engineering problem at that point. Is OpenFast need further, oh, sorry, there's a lot of things that are happening. Does OpenFast need further software to run an actuator like MATLAB or Simulink? Yes. So there's a number of different ways that we could utilize OpenFast. One is in this sort of 3-loop architecture that I've already been showing, where OpenFast is housed on its own machines and solving for the next time step. But to do that, you need to somehow separate it out. So the nice thing about OpenFast is that it's modular. So each part of OpenFast is sort of coupled together through a glue code, and those parts could be, say, the mooring dynamics, the structural dynamics, the aerodynamics, etc. And so you can imagine creating your own module, that's sort of an experimental module that you insert into that sort of already modular setup, and then communicate to the glue code. There's actually also an open source Simulink function that you can also utilize that would have OpenFast embedded directly into Simulink. Okay, let's see. In the offshore wind turbine testing, how does the correlation of the wind and the wave will be considered? Oh, that's a great question. What types of floaters will be tested? Okay, yeah, so correlation between the wind and the waves. So actually we have Bryson Robertson and his student have been looking very in-depth into the resource conditions at a site off the coast of Oregon and correlating basically the wind and the waves at that specific location. And so that's all been sort of thought about in terms of thinking about the resource condition for that specific location for the offshore wind turbine. We're focusing on semi-submersible wind turbines. And yeah, you have to make sure that whatever wind you're supplying is actually representative of the location that you're considering and the waves that are expected there. For the geographically distributed hybrid simulation, where you have, say, wind at, let's say, one of the Florida facilities and waves at, say, one of our facilities, and you're dealing with different timescales and you're supplying the wind and the wave loading at 2 separate facilities, you would also have to make sure that whatever wind and wave conditions that you're supplying at both facilities are correlated in some way. And so you can say that, for example, you can relate the storm surge to velocity, the wind velocity, but that actually doesn't account for all the possible correlations between the wind and the waves at a certain site. So you might have to actually think about doing some sort of matrix of loading conditions to sort of represent the worst case scenario. So you can say, like, for this wind velocity, I'm gonna have this wave height and potentially wave period, and then this sort of surge height, because surge is not only related to wind velocity, it's also related to pressures. And so that correlation is, of course, something that you need to think about. Have you considered the inertial? Okay, how are you considering the inertia effects in the scale model? So if I'm interpreting this question correctly, which I hope that I am, it's actually, that's actually very important point, and not exactly the easiest one. So how we typically think about earthquake simulations is when we have a model that's scaled down at small scale, typically what you end up doing is you scale up the mass to get, you know, approximately close to the structural dynamics characteristics that you want. You can do the same thing for a fixed base structure being subjected to some sort of hydrodynamic loading in terms of scaled up mass. Where this becomes more difficult is when you're dealing with a floating structure. So if you have a floating structure and now you've suddenly scaled up the mass, then you can have a significant problem in how that structure, that floating structure, is now interacting with the waves and really its buoyancy effects, and all of those need to be considered. So thinking about which part of the numerical physical subassemblies has the mass becomes really important. A lot of the studies to date, for example, and I'm sorry if I'm going through these quite fast, for example, this figure on the right is actually modeling the mass physically. And for a lot of the researchers on this call who are familiar with hybrid simulation, that could lead to maybe potentially a lack of mass in your numerical model, which could potentially lead to some sort of stability effects. So where you put that mass in the numerical versus physical system, and then making sure that whatever you do end up doing physically, still, if you're dealing with something that's floating, still has the responses that you're interested in, and becomes really important. Okay. Let's see. So what is the state of practice and design to address this wave structure interaction issue? Is through time history dynamic analysis from both wind and wave, or some sort of spectrum analysis or equivalent static analysis? Yeah, so my understanding is that a lot of times the dynamic component of this, at least in design, is neglected. Would post-yielding and inelastic soil structure interaction be often considered in the analysis? So when we're thinking about all of this from a design perspective, and we're thinking about sort of new updates to ASC 7, a lot of these considerations, particularly with regards to the fluid structure interaction effects, are not yet incorporated. Also, the time varying component of the loading, which typically in earthquake engineering we would consider through some sort of response spectrum analysis, potentially, which still has some sort of dynamic amplification effect. That's not what you would necessarily see in an ASC 7 setting. And to be fair, I am not also very familiar with the design part of this, of coastal engineering. I myself am a structural engineer with my background's in earthquake engineering. But as of right now, that is not something that's currently taken into account in design. Now, when you're starting to look at floating offshore wind platforms, then you see a lot more on the numerical side, as far as actually incorporating both wind and waves effects. For example, using the OpenFast software. So it really just depends on what industry you're coming from. And then as far as the state of practice in designing wave, wind, structure effects, often separating the wind and the wave is the status quo. So there's a lot of assumptions on whether the wind does not affect the waves, or the waves does not affect the wind, or that the wind and the wave loading can be both applied via superposition. And there's a lot of questions with any one of those assumptions, and the answer is it all depends, and it depends on which part of the problem you think is important. Any other questions? Okay. Well, please feel free to email me at any time. I'd be happy to talk more about this. As you can see, any one of these other collaborators would also have more or less information at any one part of this problem. It's really been quite a joy to work with a number of different people from a number of different disciplines. Okay. Well, thank you. And then I will stop sharing. Okay, I also don't know whether I should log off. Okay, cool. Well, I guess please feel free to email me with any questions. Love to chat with anybody more about this. We'd really like to work with anyone who's interested in sort of bringing more expertise to this problem. So with that, I will mute myself and stop my video.